Greetings, everybody. Learning is a hobby here. I want to go over my solutions to section 4.3, the exercise set for section 4.3 in Tao's Analysis 1 book, which is what I'm going to do here in this video. So let me bring up my solutions and we'll go through them. Okay, and I have the summary for section 4.3 up as well, so I can refer back to the theorems, because basically what he asks you to do in this exercise set is to prove the theorem. So let's start with 4.3, exercise 4.3.1. He asks us to prove proposition 4.3.3. Let me read out that, show you that what that theorem is, and then we'll read his hint here. So 4.3. I have to scroll up here. It's this one here. So proposition 4.3.3, basic properties of absolute value and distance. And there's a bunch of parts to it. So like we've been doing, I'll take it one at a time. So let me go read his hint. Whoops, that's not what I wanted. Let me go read his hint here. While all of these claims can be proven by dividing into cases, such as when x is positive, negative, or zero, several parts of the proposition can be proven without such a tedious division into cases. For instance, one can use earlier parts of the proposition to prove later ones. All right, so let me read out what part A says, and then we'll prove it. So part A is non-degeneracy of absolute value, which states that we have absolute value x greater than or equal to 0, and absolute value x equals 0 if and only if x equals 0. All right, so here's part A. So let x be a rational number, and that means that x is either equal 0, greater than 0, or less than 0 by trichotomy. Then we'll just take it case by case. If x is not 0, then either x is greater than 0 or x is less than 0. Then the absolute value of x is equal to x, which is greater than 0 if x is greater than 0, or absolute value x is negative x, which is greater than 0 if x is less than 0. Therefore, absolute value x is greater than 0 when x is not 0. Furthermore, if x is equal to 0, which is the last case, then absolute value x equals 0 by definition 4.3.1. And finally, if absolute value x is equal to 0, then x greater than 0 or x less than 0 implies that absolute value x greater than 0, which is a contradiction. Therefore, x has to be 0. Right. So the last part was a proof by contradiction. All right. Part B is the triangle inequality. Let me just bring it up here so you remember what it says. We have absolute value x plus y less than or equal to absolute value x plus absolute value y. So here I broke it up into cases, and actually we did prove the triangle inequality in Spivak, but in Spivak we did it for real numbers, so it's worth doing it again here, just using what we know about rationals now. So assume x greater than or equal to 0, y greater than or equal to 0, then x plus y is greater than or equal to 0 by 4.2.9 part D. Then absolute value x plus y is x plus y, which is equal to absolute value x plus absolute value y, which is less than or equal to itself. So that proves it in that case. Case 2, if x is less than or equal to 0 and y is less than or equal to 0, then x plus y is less than or equal to 0, which implies that the negation of it is greater than or equal to 0, which means that negative x minus y is greater than or equal to 0. Then the absolute value of x plus y equals the negation of x plus y, which is equal to the negation of x plus the negation of y, which is equal to the absolute value of x plus the absolute value of y, which is less than or equal to itself. Right, that proves that case. Part C, if x is, case C, so I switched from numbers to letters here. This should be case 3, I guess. And this should be case 4. No, I don't need a case 4, just a case 3. If x is less than or equal to 0 and y is greater than or equal to 0, then negative x is greater than or equal to 0. If absolute value x is less than or equal to y, then absolute value x plus y equals x plus y, which is less than or equal to negative x plus y, which is equal to absolute value x plus absolute value y. That's because x is less than or equal to negative x, right? And we had properties of the order on rationals. All right, and then the last case, if absolute value x is greater than or equal to y, then absolute value x plus y is equal to negative x minus y, which is less than or equal to absolute value x plus the negation of y, less than or equal to, that's less than or equal to absolute value x plus absolute value y. And that's the proof for the triangle inequality for all rational numbers, because we've exhausted all the possible cases. Okay. Part D is did I? Oh, I think I skipped part C. Did I? Hang on. Maybe I labeled it wrong. I think this is the proof of part C. Sorry, this should be, whoops, this should be part C here. Let me just double check. Part C says we have the inequalities negative y less than or equal to x less than or equal to y, if and only if y is greater than or equal to the absolute value x. In particular, we have negative absolute value x less than or equal to x less than or equal to absolute value x. And I have the proof for part C here. So let negative y less than or equal to x less than or equal to y, then x less than or equal to y, and negative x is less than or equal to y, which implies that absolute value of x is less than or equal to y. And if now we do the reverse direction, if absolute value x is less than or equal to y, then if x is greater than or equal to 0, then x is less than or equal to y, and y is greater than or equal to 0, which implies that negative y less than or equal to 0, less than or equal to x, less than or equal to y, which shows that negative y less than or equal to x, less than or equal to y. All right, and then if x is less than 0, then negative x less than or equal to y, and x greater than or equal to negative y implies negative y less than or equal to x, which is less than or strictly, which is less than 0, less than negative x, less than or equal to y, which implies, again, that negative y less than or equal to x, less than or equal to y. So that part I broke up into cases, obviously. The next part, multiplicativity of absolute value. Let me see, did I just label that wrong? Yeah, that one should be D. This should be part D. Whoops, this should be part D here. All right, so this says that absolute value x times y is equal to absolute value x times absolute value y. All right, so let x, y be rational numbers. Then if x is greater than or equal to 0, y is greater than or equal to 0, then absolute value xy is equal to xy because the product is positive, which is equal to absolute value x, absolute value y, so that works out. Next case, if x is negative or 0 and y is less than or equal to 0, so both negative or 0, then the product xy is the absolute value of the product of xy is equal to the negative of x times the negative of y, which is equal to the absolute value of x times the absolute value of y. And then finally, the third case, if x is greater than or equal to 0, y is less than or equal to 0, then the absolute value of the product xy is x times minus y, which is equal to absolute value x times absolute value y, just follows from the definition. All right, this should be part E down here. All right, E is the non-degeneracy of distance. So these next parts here follow similar type of propositions for the propositions about absolute value, because we define the distance in terms of absolute value. So E says we have the distance between x and y is greater than or equal to 0, and also that the distance between x and y equals 0 if and only if x equals y. All right, so we'll prove that here. The distance between x and y, by definition, is the absolute value of x minus y. That's greater than or equal to 0 by part A. Also, the distance between x and y, which is, again, the absolute value of x minus y, equals 0 if and only if x minus y is 0, which implies that x equals y. So that proves non-degeneracy. Then part F is about oops, I have symmetry here. Did I skip something? Hang on. Did I do the I think I skipped the triangle inequality for distance. Anyway, let's do symmetry here. Symmetry is part F, which says that the distance between x and y is equal to the distance between y and x. Right, so without loss of generality, let's assume that x is greater than or equal to y. Then the distance between x and y is equal to the absolute value x minus y, which is equal to x minus y, which is equal to the negation of y minus x, which is equal to the absolute value of y minus x, which shows that that's obviously equal to the distance between y and x by definition, and that shows that the two things are equal to each other. All right, so let's see, I didn't do, I guess I forgot to do the triangle inequality for distance. Let's see if we can actually work that out. I didn't leave myself space to do it. Maybe I can fit it in down here. It's a long exercise set, I guess. Let's try, what letter was that? Letter G. So this is the triangle inequality. Oops, triangle inequality for distance. Okay, let x, y, z be rational numbers. Whoops, rational numbers. All right, and we want to look at the distance between x and z, which by definition is the absolute value of x minus z. This is equal to the absolute value of x minus y plus y minus z, which by the triangle inequality for absolute value, this is less than or equal to x minus y plus absolute value y minus z, which is equal to the distance between x and y plus the distance between y and z, which is the triangle inequality. So that proves that one. Okay. Hopefully I didn't forget to do any of the other parts, but we'll see. All right, so we did that whole question. Okay, next is for exercise 4.3.2. Tao asks us in this one to prove proposition 4.3.7. Let me bring that up. All right, this is proposition 4.3.7. It's a bunch of properties of what, the epsilon closeness concept that we talked about. So let XYZ be rational numbers. Again, we'll just prove it case by case. So part A is if x equals y, then x is epsilon close to y for every epsilon greater than 0. Conversely, if x is epsilon close to y for every epsilon greater than 0, then we have x equals y. So let's do that one first. So let's assume that x equals y by, for our hypothesis, and that epsilon is greater than 0 is given, then the distance between x and y is equal to the absolute value of x minus y, which is equal to 0 because x equals y by hypothesis. And remember, the absolute value of 0 is 0. And obviously that's less than or equal to any positive number epsilon. And next, let the distance between x and y be less than or equal to epsilon for every epsilon greater than 0. Then the distance between x and y has to be equal to 0 by non-degeneracy. Okay, that's part A. Part B says let epsilon greater than 0. If x is epsilon close to y, then y is epsilon close to x. Okay, so here's the proof for part B. Let epsilon greater than 0 and xy be rational numbers such that the distance between x and y is less than or equal to epsilon. Then the distance between y and x is equal to the distance between x and y, which is less than or equal to epsilon by symmetry of distance. Therefore, y and x are epsilon close when x, y are epsilon close. Right. Then part C says let epsilon delta greater than 0. If x is epsilon close to y and y is delta close to z, then x and z are epsilon plus delta close. All right, let epsilon delta greater than 0. and also x, y, z be rational numbers such that the distance between x and y is less than or equal to epsilon, and the distance between y and z is less than or equal to delta, then the distance between x and z is less than or equal to the distance between x and y plus the distance between y and z, which is less than or equal to epsilon plus delta, and that shows that the distance between x and z is that x and z are epsilon plus delta close. All right, part D. Let epsilon delta greater than 0. If x and y are epsilon close and z and w are delta close, then x plus z and y plus w are epsilon plus delta close, and x minus z and y minus w are also epsilon plus delta close. Okay. Let epsilon delta greater than 0 and x, y, z, w rational numbers such that the distance between x and y is less than or equal to epsilon, and the distance between z and w less than or equal to delta. Then the distance between x plus z and y plus w is equal to the absolute value of x plus z minus y plus w, which we can rearrange by commutativity and associativity of addition of rational numbers. So I can rearrange things to the absolute value of x minus y plus z minus w, which is less than or equal to the absolute value of x minus y plus z minus w by the triangle inequality for absolute value, which is equal to the distance between x and y plus the distance between z and w, which is less than or equal to epsilon plus delta. Therefore, x plus z and y plus w are epsilon plus delta close. And it looks like I skipped the other part, the what was the other one they wanted? X minus z and y minus w, but you can do it the similar way. So I'll just skip that one. Part E, sorry, I have to read it out. Part E says, let epsilon greater than 0. If x and y are epsilon close, they are also epsilon prime close for every epsilon greater than, for every epsilon prime greater than epsilon. All right, so let 0 less than epsilon less than or equal to epsilon prime. Let x, y be rational numbers such that the distance between x and y is less than or equal to epsilon. Then the distance between x and y is less than or equal to epsilon by hypothesis. But epsilon also by hypothesis is less than or equal to epsilon prime, which means that x and y are also epsilon prime close. Right, part F says let epsilon greater than 0 if y and z are both epsilon close to x and w is between y and z. Here he suggests that means y less than or equal to w less than or equal to z, or the other way around. Then the conclusion here is that w is also epsilon close to x. So here's my proof. Let epsilon be greater than 0, x, y, z, w, rational numbers such that the distance between x and y is less than or equal to epsilon, and distance between x and z less than or equal to epsilon. And without loss of generality, we can assume that y is less than or equal to w less than or equal to z. Then if we subtract or add the negative of x to all three sides, the order is preserved, so we get y minus x less than or equal to w minus x less than or equal to z minus x, which implies that either absolute value y minus x is less than or equal to absolute value z minus x, or the other way around. In the first case, the distance between x and w is equal to the absolute value of x minus w, which is less than or equal to the absolute value of z minus x, which is the distance between x and z, which is less than or equal to epsilon. And in the second case, same thing. It's just you use the upper bound x, the absolute value x minus y. Therefore, x and w are epsilon close. Right, part G says let epsilon greater than 0 if x and y are epsilon close and z is non-zero, then xz and yz are epsilon times absolute value z close. Right, so here's the proof. Let epsilon greater than 0, xy rational, such that the distance between x and y is less than or equal to epsilon, and z is a rational number, such that z is not 0. Then we'll look at the distance between xz and yz. By definition, that's the absolute value of xz minus yz. And then by the distributive law, that's the same thing as the absolute value of z times x minus y. And then we could just break that up by multiplicativity of absolute value. That's equal to absolute value z times the absolute value of the absolute value of x minus y, which is the absolute value of z times the distance between x and y, which is less than or equal to absolute value z times epsilon, and that shows the property. Right, and then lastly, for part H, he actually proves this in the book, but I'll show you his proof. Part H says, let epsilon delta greater than 0. If x and y are epsilon close and z and w are delta close, then x, z, and y, w are epsilon times absolute value z plus delta times absolute value x plus epsilon delta close. So let me show you his proof, because he does it actually in the book, but I didn't write it over in my notes. I wanted to have everything here together in one place. So let epsilon delta be greater than 0 and x, y, z, w rational numbers such that the distance between x and y is less than or equal to epsilon and the distance between z and w less than or equal to delta. Then we can define the number a to be y minus x and the number b to be, it should be equals here. B is equal to w minus z, then y equals x plus a, and w equals z plus b, and the absolute value of a is less than or equal to epsilon by hypothesis, and the absolute value of b is less than or equal to delta by hypothesis. Then the distance between x, z, and y, w, by definition, is the absolute value of xz minus yw, which is equal to xy minus, here we can replace y with x plus a, and we can replace w with z plus b, and then just simplify inside the absolute value, which gives you absolute value az plus bx plus ab, which is less than or equal to the absolute value of az plus absolute value bx plus absolute value ab by the triangle inequality. And then by multiplicativity, that's hard to say, is equal to absolute value a times absolute value z plus absolute value b times absolute value x plus absolute value a times absolute value b, which is less than or equal to epsilon times absolute value z plus delta times absolute value x plus epsilon delta. And that proves the last part H. Okay, and then next question, 4.3.3 says prove proposition 4.3.10. He does give a hint here. He says use induction. Let me just remind you what this proposition says. Right here, this is the properties of exponentiation, part 1. Remember, there's also a properties of exponentiation, part 2, which we'll also prove after this question. So there's a bunch of parts to this. Let's just do them one at a time. Let x, y be rational numbers, and let n, m be natural numbers. Part A says we have x to the n times x to the m is equal to x to the n plus m. X to the n to the m is x to the n m, and x, y to the n is x to the n times y to the n. The usual properties of exponents. Here we're assuming that the exponents are natural numbers, though, so we can use induction. So for part A, proceed by induction on n. I'm going to fix a natural number m, so the power m will be a fixed power. All right. Base step, n equals 0, x to the 0 times x to the m equals 1 times x to the m by the way we define x to the 0, which is equal to x to the m because the multiplicative identity doesn't change the value when you multiply by it, which is equal to the number x times, x to the m plus 0 power. All right, that's the base step satisfied. Then we go to the inductive step. Assume that x to the n times x to the m is x to the n plus m for some natural number n, and consider x to the n plus 1 times x to the m. That's equal to x times x to the n plus x to the m, which is x times x to the n plus m. By inductive hypothesis, that follows, which means that x times x to the n plus m is equal to x to the n plus m plus 1, which is the same thing as x to the n plus 1 plus m. That therefore the property holds by mathematical induction. Then we go on to the second property, which is the power to a power rule. So x to the n to the m is x to the nm. And again, we do this with induction. So base step n equals 0. X to the m to the 0 power is equal to 1 because anything to the 0 power is defined to be equal to 1, which is equal to x to the 0. So, and x to the 0 is the same thing as x to the m times 0. And also it works if you do it in the opposite order. So x to the 0 to the m is 1 to the m power, which is equal to 1. So notice that they both equal the same thing. right? Inductive step, assume x to the n to the m is x to the nm for some n in n, and x to the m to the n equals x to the n plus, and x to the nm. Then x to the n plus 1 to the m is equal to x times x to the n to the m. That's equal to x times x to the n, dot, 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 all the way down to the last factor of x times x to the n. There's m of those factors. And then just using associativity of multiplication, that's the same thing as and commutativity. That's equal to x multiplied by itself m times, and x to the n multiplied by itself m times, which is x to the m times x to the nm by inductive hypothesis. And that's equal to x to the nm plus m by part 1. And if you just factor out the m from the power there, you get x to the n plus 1 times m. And same thing works in the opposite order. So if you look at x to the m to the n plus 1, that's x to the m to the n times x to the m, which is x to the n m times x to the m by inductive hypothesis, which is the same thing as x to the n m plus m. And then again, you can factor out the m, which gives you x to the m plus 1 times m in the power. Right, so the property holds by induction. And then for the last part here, exponentiation by natural number powers distributes over multiplication. Right, again, base step n equals 0, x, y to the 0 is 1, which is the same thing as 1 times 1, which is the same thing as x to the 0 times y to the 0. Inductive step, assume x, y to the n equals x to the n, y to the n for some n in n. Then x, y to the n plus 1 is x, y to the n times x, y, which is x to the n, y to the n, x, y by inductive hypothesis, which is equal to x to the n, which implies x to the n, y to the n, xy equals x to the n times x times y to the n times y, again, just by commutativity of multiplication, which is equal to x to the n plus 1 times y to the n plus 1 by definition of exponentiate, the way we define exponentiation recursively. All right. Then we can move on to part B of the proposition, which says that if n is greater than 0, we have x to the n equals 0 if and only if x equals 0. All right, again, all these are going to be by induction, so we induct on n. Here we're going to start with n equals 0 because we're assuming that n is greater than 0. So x to the 1 equals 0 obviously implies that x equals 0. So the base step is satisfied. Then we go on to the inductive step. So assume x to the n equals 0 implies x equals 0 for some natural number n. Then x to the n plus 1 is equal to, sorry, we just want to make sure that I didn't sit on the volume. Okay. X to the n equals 0 implies x equals 0 for some n and n. Then x to the n plus 1 equals 0 implies x times x to the n equals 0. And by the fact that the rational numbers have no zero divisors, that means that x equals 0 or x to the n equals 0. And in both cases, that leads to x equals 0. Right, part C. If x greater than or equal to y greater than or equal to 0, then x to the n greater than equal to y to the n greater than or equal to 0. If x greater than y greater than or equal to 0 and n greater than 0, then x to the n greater than y to the n greater than or equal to 0. All right, so let's prove that one. Again, it's by induction on n. Let's start with the base step, n equals 0. Let's assume that x is greater than or equal to y, greater than or equal to 0. Then x to the 0 obviously is equal to 1, and y to the 0 is equal to 1 by definition. And obviously 1 is greater than or equal to 1 is greater than or equal to 0, so the base step is satisfied. Then we do the inductive step. Assume x greater than or equal to y, greater than or equal to 0. That implies x to the n greater than or equal to y to the n, greater than or equal to 0 for some natural number n. Then we consider x to the n plus 1. That's the same thing as x times x to the n, which is greater than or equal to x times y to the n by inductive hypothesis, which is greater than or equal to y times y to the n, which is y to the n plus 1, which is greater than or equal to 0 times y, which is 0. So that shows that the proposition holds. I won't go through the second one, in detail because it's virtually identical to the one I just did. You can pause your screen here and read it if you want to, but I'll move on to part D. We induct on n. Oh, let me read it out first. We have absolute value x to the n equals x to the absolute value x to the n. So again, induction n equals 0, x to 0 is 1, which is the same thing as absolute value x to the 0. So that works. Inductive step, assume absolute value x to the n equals absolute value x to the n power for some natural number n. Then consider absolute value of x to the n plus 1. That's the same thing as absolute value x times x to the n, which is equal to absolute value x times absolute value x to the n, which is equal to absolute value x times absolute value x to the n by inductive hypothesis, which is equal to absolute value x to the n plus 1 by the recursive definition. All right, and that proves that proposition. Right, next we're going to go on to prove proposition 4.3.12, which is very similar to the one we just did, except now we're allowing integer exponents. So here's the proposition that he's asking us to prove, properties of exponentiation. Part 2, here we're going to assume that x and y are non-zero rational numbers, and that the powers n and m can be integers rather than merely natural numbers. All right, part A is similar to the part A in the previous proposition, so we want to prove that. But here, we're not allowed to use induction because if you remember, we showed in the chapter that induction doesn't hold in general for integers. So we have to actually, in this case, use proposition 4.3.10, which is the one that we just proved. Okay, so here's the proof. Let x, y be non-zero rational numbers and n, m be integers. Then since we already know that properties A through D hold for non-negative integers, we can assume that n and m are, at least one of n and m are negative. So let's do part A. So the first part is, so here I'm going to assume that negative n is less than 0 and m is greater than 0. Then x to the minus n times x to the m is equal to 1 over x to the n times x to the m by definition, which is equal to 1 over x to the n times x to the m. That's 1 over x times itself n times, and we have x to the m is x times itself m times, and then we could just use the commutative law and the associative law to re-associate things. Then we get 1 over x times itself n times. All of those are equal to 1 because when you multiply reciprocals by each other, you get 1. That was by the field axioms that he didn't call them axioms. It was a proposition for the rationals, but we know that holds for, I think it was like part 10 of that theorem. But anyway, all of those are equal to 1, and then we're left over with n minus n factors of x. So we have 1 times x to the m minus n, which is x to the m minus n. Right, and then if both of them are negative, if both powers are negative, then x to the minus n times x to the minus m is 1 over x to the n times 1 over x to the m. And then by the definition of multiplication of rational numbers, that's 1 over x to the n x times x to the m, which is equal to 1 over x to the n plus m. We already know this for positive rationals, and that's equal to x to the minus or the negative of n plus m, which is the same thing as x to the minus n minus m. Right, for second exponentiation rule, again, here I'm doing it in cases. Let n, if at negative n is less than 0 and negative m is less than 0, then x to the minus n to the minus m is 1 over x to the n to the minus m, which is x to the n to the m, which is x to the nm. Right, and then if one is negative and the other positive, so assume negative n is the negative one, then x to the minus n to the m is 1 over x to the n to the m power, which is equal to 1 over x to the n times itself m times, which is 1 over x to the n to the m. And we know that that's equal to 1 over x to the nm by the previous proposition, which is equal to x to the negative of mn, which is x to the negative n times m. Okay, and if n is positive and m is the negative one, then x to the n to the minus m is 1 over x to the n to the m, which is 1 over x to the nm by the previous proposition, which is equal to x to the negative of nm, which is x to the n times negative m, and that proves that property. Finally, for part 3, here we want to show that xy to the n powers x to the n times y to the n for integers. So here assume that negative n is less than 0, and consider xy to the minus n. That's equal to 1 over xy to the n by the definition, equals 1 over x to the n times y to the n by the previous proposition, which is 1 over x to the n times 1 over y to the n, which is x to the minus n times y to the minus n. And that proves that part. All right, part B says if x is greater than or equal to y greater than 0, then x to the n greater than or equal to y to the n greater than 0 if n is positive. I'm not going to prove that because we already showed it in the previous proposition, but the second part we need to show. And 0 less than x to the n less than or equal to y to the n if n is negative. So let's prove that second part. So let x greater than or equal to y greater than 0 and negative n less than 0, then x to the n greater than or equal to y to the n greater than 0, and x to the minus n times y to the minus n is greater than 0, which implies that here I'm multiplying everything by x to the minus n times y to the minus n. When you simplify everything, you get y to the minus n is greater than or equal to x to the minus n greater than 0, and that proves that part. All right, part C, if xy greater than 0 and n not 0, and x to the n equals y to the n, then x equals y. All right, let xy greater than 0 and negative n less than 0. Assume x to the minus n equals y to the minus n, and that x not y. Then without loss of generality, assume that x greater than y greater than 0. Then 0 less than x to the minus n less than y to the minus n, by what we just showed up above, which contradicts that x to the minus n is equal to y to the minus n, therefore x has to equal y. Okay, last part for this proposition, part D, is similar to the one that we did up above, except now again we're allowing integer exponents. So let negative n less than 0, then x to the minus n in absolute value is 1 over x to the n in absolute value, which is equal to 1 over x times itself n times in absolute value. That's equal to the absolute value of 1 over x times itself n times, which is the same thing as 1 over absolute value x n times, which is equal to 1 over absolute value x to the n, which is equal to absolute value x to the minus n, and that proves that part. Okay, and last problem here is not one of the propositions. He wants us to prove that 2 to the n greater than n for all positive integers n, and he gives a hint. He says use induction, so we'll do that. Induct on n, base step n is 0, works because 1 is equal to 2 to the 0, which is obviously greater than or equal to 0. And then the inductive step, assume that 2 to the n is greater than or equal to n for some natural number n. Consider 2 to the n plus 1, that's equal to 2 times 2 to the n, which is greater than or equal to 2 times n, which is equal to n plus n, which is greater than or equal to n plus 1, and that proves the theorem. Okay, and that's the exercise set for 4.3. All right, so I'm in the middle actually of writing up my summary for section 4.4. That should be up, the video for that should be up tomorrow at some point, and maybe even the exercise set, because the exercise set is kind of short for the next section. So I'll see you guys in the next one, which will be like I said, the last section of chapter 4. So we'll be done with chapter 4 this week. So I'm pretty excited about that. I'll see you guys in the next one. Keep learning until that point.